We have seen in a previous video how to instantiate templates to create a bridge. If you are wondering how to create those templates, you are in the right video. I will show you in this video how to create a low LOD template, a user feature, but it could be any other kind of template that will be compatible with the Bridge Design Assistant. This is based on the civil engineer role and civil 3D design application. I'll start by creating a new deck from new content. I will then insert a skeleton. A skeleton is the equivalent of a 3D shape, but with specific properties. For example, it is not projected by default in a drawing and not taken into account for clash analysis. It is for construction geometry usually. First, I need to define the inputs of my pier. So I create a specific geometrical set. I will define three inputs: a curve, a start axis system, and an end axis system. It is better to have simple inputs than reusing complex geometry to improve the performance during instantiation of your components. This is why I create a basic spline through 3 points to define my alignment input. It is a good practice to isolate the inputs that will be replaced by real geometry at instantiation, here an alignment. I will create 2 points for the start and end of my deck. It is better not to have those at the extremity of the curve so that we can manage a skew angle for the deck if necessary. I can create axis systems on those points and, first, constrain them with the vertical z-axis and the x-axis in the direction of the curve. I change the geometrical set for the axis systems and isolate them. In the online documentation, you can find some naming convention for the Bridge Design Assistant under 3D modeling, multidiscipline engineering, civil engineering 3D design, bridge design, and about the Bridge Design Assistant. It is mentioned there that it is mandatory to have the start axis system to be named base axis system. Optionally, the end should be named end axis system and the curve should be named alignment. So I rename my axis systems accordingly. Now that my inputs are set, I create a new geometrical set that will contain the deck geometry I want to define as my template. First of all, it is a good practice to create a formula to link the inputs with my geometry. This allows to grab all the axis system information in one shot, such as the different planes, the origin, the axis, and so on. I can create new parameters of curve or axis type and add a formula pointing to the inputs. I'll rename my formulas. There is no naming convention there. Once created, I can hide my input set so that all the geometry I pick will be related to the formula I just created. Instead of having my parameters and formulas stored in the global parameter and formula sets of my part, I can add new parameter and formula sets into my geometrical set with the application engineering rules capture. I can now define the profile of my deck on the YZ plane of my start axis system. You can define your own geometry there. Here, I'm creating a simple deck segment. After creating a rough profile, I create constraints such as coincidence using the right-click menu, symmetry, distance, length, symmetry again, and two more lengths. Since the deck size can change from one project to another, I want to be able to drive the different lengths of my deck at instantiation. I then create parameters to drive the width on top and at the bottom, the height and flange height. In the same documentation chapter as before, we can notice that there is a table to map your template parameters with the bridge global parameters. We see that the height of the deck should be named height, and it is not mentioned here, but the width of the deck should be named width. So I rename my parameters accordingly and choose the name I want for the parameters that are not defined in the table. Now I can link the constraint of my sketch to those parameters through a formula. My profile is done. I can then sweep this profile along the alignment curve with the z-axis as pulling direction. As you can notice at the end extremity, the sweep is done perpendicular to the alignment. This means that the end face of the deck is not vertical. We do not want this to happen, so we will add a spine to the sweep. To create the spine, I project the alignment on an horizontal plane, here the XY plane of the base axis system. I set it as the spine and relimit the volume sweep by my two-axis system. Notice that now the end face is vertical. I can add a volume parameter that will measure the volume of my swept deck. This will be really helpful to automatically get the quantities and takeoff for my bridge. I move the volume parameter in my parameter set and rename it. Now, I will manage my deck outputs that will be used by the other bridge component such as piers and abutments. Still in the documentation, I can see under the decks that two output axis systems should be generated as input for support 1 and input for support 2. They will be used to instantiate the piers and abutments. Similarly, the abutment might require deck faces, here front 1 of the span, front 2 of the span. We will first generate the output axis system that should be located at the bottom of the deck. So I translate first my alignment toward the bottom using the height parameter so that this operation is updated if the deck size is changing. I then intersect this alignment with the start and end YZ plane to create the origin of my output axis system. I can then create the output axis systems and constrain their orientation to follow the one of the start and end axis systems. Finally, I create a fill of the profile sketch and define it as the front one of the span. I copy this sketch and change its reference plane to the YZ plane of the N-axis system. I can again do a fill and rename it front 2 of the span. I hide all the construction geometry to only display the deck volume. I move all the formulas with drag and drop to my formula set. I can now create my user-defined feature. Since I put all the data I wanted to add in the deck geometry geometrical set, when I select it, all the right inputs have been identified. I check that the names of the inputs are correct. I publish the parameters that I want to be able to drive at instantiation by double-clicking in the published column in front of the parameter. I add also the volume so that it will be visible as an output of my UDF. I then manage the outputs. The main output should be the deck volume. If it is not the case, use the replace. I add other outputs such as input for support axis systems and front of the spans. My deck UDF is ready. I can save. The last step is to create a deck object type so that I can reuse this template with component-based design. The object type should be adaptive, meaning that it will morph at instantiation with its inputs. It will follow the alignment. I double-click on the resource table and assign my UDF as feature-based design resource by right-clicking on the resource field. This will be my low LOD representation of the deck. We will see in the next tutorial how to create the high LOD template, the engineering template, that will be assigned in the last line of the resource table. Do not forget to save. Let's test our new template with the Bridge Design Assistant. For more information about the Bridge Design Assistant, please check the previous tutorial. Parameters values are different than the one set in my template. I assign the template I just created as deck template. My template is instantiated. I can perform changes, such as moving axis systems, and changing parameters, such as height and width. And everything updates. Finally, I can extract all my deck volumes using a knowledge report. Now, you can generate your own templates. Same principle can be used for any kind of templates, not only bridges. Enjoy!